be best if we kick this started. We've got a pretty hefty slide pack to go through, so the sooner we start, the better. So yeah, thank you for joining us today. Today is the official launch of the National Composite Center Technology Pull-Through program for next year. Just so you know, this presentation will be recorded as started actually, and it will be posted on the NCC website after today. So if you have to drop off midway through the presentation, feel free to do so, because you'll find it again later, should you need to go back to this. And we will also be sharing the slides, so you'll have the opportunity to go back into the details, because I don't expect we're going to have enough time to go into the nitty-gritty of specific elements today during the launch webinar, but you'll have the opportunity to go through the slides at your pace later on. Can I have the next slide, please? We've got the agenda here. I will be giving you a brief introduction on the program. Roger Walker, our technology program manager, will walk you through the process on how to apply and how to make it happen. And then we've got 4 champions from the NCC that will be mapping out the key areas that we have identified as themes and topics to capture research work on, and they will be outlining the knowledge gaps that they have identified in their respective fields. We'll be concluding hopefully at around 10:30, so in about an hour from now, and we'll finish soon after that with a bit of a summary. So if I can go to the first slide straight after this, please. Okay, so for those of you that don't know me, my name is Giuseppe Dell'Anno. I am now at the NCC part-time as an academic liaison, hence my reason to be here today. I've recently rejoined the NCC after having spent about 8 years in the center from the very inception of the National Composite Center. So I've got a bit of history with the center. We have launched the technology pull-through in 2017. Can I have the next slide, please? So this is going to be effectively its 8th iteration, and the NCC is the only center at the moment out of the high-value manufacturing catapult centers that runs such a program, although there is a lot of effort going on at catapult level to extend the NCC program horizontally across the 7 sister companies that you see listed on the slide, and even vertically all the way up to cross catapult. That is very much work in progress as we speak. The National Composite Center, as you can see here, as I said, is one of 7 sister centers, all with different specialties in the manufacturing space. And together we make up the high-value manufacturing catapult, one of 9 catapult networks that have been established in the UK about 10 years ago. And you've got some stats there to give you some ideas of what the HVMC as a whole delivers and is made up of in terms of people, technologies, and impact in the manufacturing space in the UK. Next slide, please. Now, the focus point of all of the catapult centers, and the reason why they are called catapults in the first place, is to focus on the mid-TRL space when it comes to technology development. This is what is called amenably the Valley of Death. If you want to stick to any macabre lingo, is essentially a space where the technologies have already matured enough in the academic environment and then are ready to be launched into the commercial and industrial space. It's typically an area where technologies are more likely to fail, and it's typically an area where the funding streams are sparser compared to the lower TRL and the higher TRL, where academia and industry are more willing to invest their own time and their own effort. And that's the reason why the catapults came about in the first place. Technology pull-through, and we'll tell you everything about this later on. Roger will cover this specifically in the next few slides. Focuses on the early stages of this midland, if you like. So a TRL 3 to 4. That's what's called the crevasse of doom, just to use even more happy lingo, where the technologies are actually ready to move out of the academic space. Next slide, please. When I joined the NCC back in 2013, it was just the 80 of us, and the NCC was half the size that it is, well, less than half the size that it is today. Today, together with our closest neighbors, which is the BCI, the British Composite Institute in Bristol, Bristol Composite Institute, we make up probably one of the largest composite hubs in the Western world, with 600 plus composite specialists. The investment in capabilities in the center have been very, very generous, and you can see by walking around the center what that means. But crucially, we've supported a lot of commercial organizations over the years, and we've partnered with several academic representatives, the best in this space, not only nationally but also internationally. Next slide, please. Okay, this is just to give you a bit of an overview of what you would find by walking through the center. There is a lot of investment in the center that is focused on automated material deposition, and you've got here a few examples that use a range of materials, from thermoplastic to thermoset, from dry to impregnated, in a range of formats, from very narrow 1/4 of an inch tapes all the way to very broad goods. However, what I'd like to add onto this slide is that the NCC capability is way beyond just the shiny pieces of equipment. It's really in the brains of those hundreds of experts that sit in our offices. And the biggest change I've seen in my 3 years of absence from the NCC is specifically in the hydrogen storage space. You'll have more on that later on, but we now have facilities to make and test our pressurized and cryogenic tanks on site, which is a big step forward in the hydrogen direction for the UK economy. I'm not going to dwell on any of these specifically, and I'm ready now to pass on the stage to Roger, who will talk you through the process for the application process.
Thanks, Giuseppe. So good morning. As introduced, I'm the Technology Program Manager, and the TPT program falls under my team. Next slide, please. So Giuseppe's given you a good overview of the centre and of the various areas along that TRL journey that innovation can fail. What the NCC has made an effort to do right from the very start is to provide the opportunity and the environment for innovation to flourish, and more importantly for the conversation today, the funding for innovative technology to be drawn from TRL 3 and 4 and actually move much further towards an industrialized solution. So it's a formal program that we run on a yearly basis. So this is our yearly kickoff. The projects are up to 12 months long, funded and managed by ourselves at the NCC, and conducted, says primarily, each project has its own kind of loading, but we look to have our researchers supporting academia to draw these projects through. The background IP stays with the source universities. The foreground IP is shared. So moving on. So a little bit about the history. As mentioned, it started in 2017, and every year there have been multiple projects undertaken. I think we are currently at around the 23 plus technologies matured, including some which I would hope are moving now somewhat into familiar territory, continuous tow shearing, hyperdiff, amongst others. So as you can see, some of these have now resulted in spin-outs from their home universities, and yet more that we worked on were actually drawing through internally within the NCC as well. As you can see, there's a variety of universities have been successful on this process and taken advantage of this opportunity to actually launch some of their innovation. As a result of this workshop, we're expecting a flurry of very, very relevant and very topical submissions for this project. We do have a limited pot of funding, so every year we go through a very rigorous down selection process. We do work with the SimCom KEC to give an external view of the academic submission, and it's then also reviewed by our chief technologists internally before we come down to a very, very select few that we will launch. There you go, the important bit. Over the years, there's a significant amount there. 2.2 is the total. It's been invested in upcoming technologies over the last 5 years. So it is an ongoing commitment by the NCC, and it is a regular activity that we do undertake. Okay. So just looking back over the history, really what I want to use this slide for is just to point out the sheer variety of submissions that this has attracted. So over the years, as we've put out our key technical challenges, they have appealed to different researchers from different universities from different parts of the UK. So we welcome that and hope that carries on with a wide variety of engagement. Okay, coming on to the relevant one then this year. As we said, this launches now in terms of this webinar, but the actual projects generally start in April. This year we have kicked off 2 projects, both directly aligned with our strategy, as we said. Our current strategy, which you will have our subject matter experts talking to you about, is materials and sustainability, composites for net zero, digital and AI, and defence. So the 2 projects this year, it's an animation there, Matt. Really helped us look at where these sit in our current technical challenge themes. So as I said, those are our 4 themes. They're driven from our market pull, so our chief engineering engagement with market drivers and sector trends, and then our technology push, our real deep scientific technology engagement to look at actually where the future needs to be and where we need to be leading. Next slide. Okay, so this year's, we've got a great one that's on the doorstep, Envision Carbon, and that's looking at inductive sensing for inspection of carbon fibre manufacturing. So working with Dr. Hughes at the University of Bristol and our own Per Saunders. And that's looking at really just changing, looking at alternative ways of getting that inspection into inline processes. So that's eddy current testing is the technology that it's looking at. And we are looking at that, applying that alongside 2 of our current capability development programs. So that's looking potentially around the hydrogen pressure vessel manufacture and potentially pipes or another continuous process. So looking at that in process NDT. Okay. And then the second one, which is pretty exciting as well, actually, it's looking at taking some of the great work that's been done out of University of Hertfordshire with Dr. Wren and Professor Hogg, and looking at addressing one of the main problems with using ceramic composites at high temperatures, which comes into the manufacturing costs and material costs. So this is looking at using that in a BMC format So looking at a moldable solution, intent there to prove that reduced cost of manufacturing, to prove how that can help increase the production rate and the complicated shapes that can be achieved, and also address some significant issues with industrializing this kind of material, with the actual mold tooling, the release process, and post-curing, how you actually support these structures once they are kind of B-staged. So that's just a bit of a run through of the two projects we've got running. Next slide. So I think we've covered most of this, but we will continue. This is the launch. The main themes you can see there remain the same. The selection criteria, which is sound understanding of the technology readiness level, strong alignment with our technology challenges, an understanding of the viability and impact for future industrial application, and also a good understanding and an agreement around the intellectual property and freedom to operate, particularly. So all very, very transparent, very straightforward ahead. Next slide. And the important piece about the timeline. So we start running today. Expression of interest form will be circulated. So from the website, there will be a form that you can submit your ideas on. Key dates there. I won't go through all of them, but I think the first one to bear in mind is the 8th of November, so 1 month from today, an expression of interest submission deadline. So please do aim for that. If there are any issues, please talk to us. I think it's the important thing. And all of that then with a view to an April 25 project start. I think that's me, and I'll hand over to our first theme. Tim.
Hi. Well, start on the next slide, please. So I'm just going to present really around the advanced materials and sustainability areas. I've gone into quite specific, so I'm going to miss out some of the whys and the detail. I think it'd be interesting if you've got ideas, we can follow up on greater fits. But what we've really got are 3 key strategic kind of materials focus areas, underpinned by a huge amount of activity around life cycle assessment, but really bringing that up to actually a whole system level understanding. So the core or common factor across all these 3 things is around the fact that the national challenge at the moment is around supply chain resilience and the sustainability of the material supply. So that's kind of, you'll see that in the theme that's going through. So if you go to the next slide, please. So there's 2 slides on CMCs, because it's largely broken up into 2 key areas. The first is oxides. So we've done a lot of work. That's where we started our CMC journey at the NCC. We have got to quite a mature place with some of the parts, but we are embarking now, as you can see from some of the targets, on a real exercise to understand how to get better cost reduction so it can actually be exploited into aerospace and we can support supply chains. So jumping out of us, and this isn't completely sort of prohibitive to other areas that we might be interested in, are 3 main technology challenges. We've got a target trying to reduce the cost for CMCs, oxide CMCs, by about 3. We need to start incorporating new oxide materials. To date, most of the work has been with established systems. Actually, there are a lot of variant systems in terms of different producers, different early academic design, material designs. But we've also got the accompanied characterization and modeling requirements. And then the last one is a challenge of actually, once we get the components and the parts, how we then join them and assemble. So all the interfaces, things like in fatigue environments, etc. So there's some key technology areas that if there's work in, that would be quite interesting. If we go to the next one, please. Very similarly, so what we're talking about in non-oxide are very high temperature. So think bordering on ultra high temperature CMCs is one example of a major theme that we're working in. Principally, it's around energy and national security. But what we're really looking to do is to really expand that out from just beyond the defence sector. This is slightly earlier in its development, so we are manufacturing parts. We haven't got onto TRL 6 yet, so there are some fundamentals that we can explore from very similar to oxides, but specifically actually bringing the materials and getting the mechanical performance right. There's some ideas on the bottom left that you can have a look at for later, some ideas that come out from the team, different cooling mechanisms, joining, actually even how we produce the CMCs in the first place. What we're really trying to target, just out of interest for next year, is that we've got a non-oxide furnace. So we can start to actually then make some parts on site. If you go to the next one. So some of you may be aware of a major program we have at the NCC developing at the moment around a pilot line. So this is a 20, 30 metre length oxycarb line and a spinning line. This is all about how we support UK production of carbon fibre and the innovation of low carbon, or that's the wrong word, net zero and defossilized performance fibre. We want to see the products that we make in the UK be a lot more sustainable. This is a major impact area that we can have, we can make strides towards. We're aiming to have an operational line beginning of 26. So that will be where we're doing the work. We're very interested in pull-through activities where you're doing research around novel architectures, improving the performance, and also how we actually verify and model the systems. What we'd like to do, I think for this particular one, is we're really trying to understand the target of where you're going with it. So a bit more blue sky might be of interest as well. If you go to the next slide, please. And then finally, oh no, sorry, not finally, there's some carbon accounting. I'll whiz through this quickly. Sorry, could you move back to the circularity slide, please? So just on this one, we've spent the last sort of 5-6 years working in recycling technologies, how we deal with end-of-life challenges. We are now embarking on a big exercise to try and build the case, so particularly moving it beyond technology, but we would still welcome technology incubation ideas, particularly if they support continuous fibre testing that we're doing at the moment, and we've got a big program of scenes that you may have heard of. So the list of technology ideas that have come through at the moment are in the middle. One of the new one that's come out would be particularly interesting around reducing the energy consumption of the actual reclamation process and joining and splicing of tows. So novel ways of doing that that are effective. If you go to the final slide, please, for this one. And then on system level LCA and carbon accounting, this is a major area to gear up for. To be really clear, I've put this in the bottom right-hand corner. The big challenge we have here is that it's not cost effective, it's very expensive, the data isn't trusted, and we're not really embracing the digital tools that we could do to make this widely adopted. I won't say any more because hopefully that's clear enough, but anything that you've been working on that might help industry adopt and it to be used more widely would be welcomed. Thank you. That's it. That's it for materials. I think we're moving on to Matt next.
Thank you, Tim. Hopefully you can hear me okay. My name is Matt Scott. I'm the Chief Technologist for Strategy at the NCC. I'm actually here on behalf of Marcus Walsbrook, who couldn't be here to present his needs. I think it's fair to say we've made some really fantastic strides over the last 5 or 6 years in hydrogen. What I'm going to talk about are some of the key drivers for us, some of the things that we're really focused on, but also I think Marcus would clarify this isn't the be all and end all. If there are other things that potentially would be very novel and exciting for the NCC to sponsor and get on board behind, please do let us know, make a submission so that we can review it. But what I will do is talk about our specific strategy areas that we are focused on, as I say, because that's really what's put us in the position that we are today, and that's what we're thinking will take us forward over the course of the next 5 years, really. So without further ado, I'm going to talk about hydrogen. I suppose the other thing that I should mention is that I'm focused really on hydrogen in this section. We have interest around sort of a wide remit of clean energy. Composites for net zero is the badge that we're using. But I think what I want to talk about today really is hydrogen. So as I say, we've made some great strides over the last 5 or so years. Our 3 focus areas are products. They are pressure vessels for storing hydrogen at very high pressures, cryogenic tanks, obviously storing hydrogen at low temperatures in order to increase its density, useful in areas like aerospace, and finally distribution pipes for transporting hydrogen over long distances. Again, I'm going to be focusing on these first 2 today. That's what we'd particularly like innovations from the academic community just now. As I say, this has come off the back of a multi-year strategy. Some of the dates in these screenshots aren't quite right, but it has been a specific vision set out, the impact that we want to see, and some milestones in order to achieve that impact. Just to say that it's been part of quite a long-term strategy, these slides. And where you can see we've reached is in the cryogenic space, and in the blue sort of box there, you can see that we've developed our own cryogenic tanks. We're putting them through cycling tests at the moment with liquid hydrogen. So all very exciting for the NCC, understanding the characteristics of how those tanks behave at low temperatures, and cycling at low temperatures, and how they can lose performance as well. And then in the green there, that's the high pressure tanks. We have a filament winder at the NCC now, which is able to produce tanks at reasonable rate and quality that are representative of industry as well. And you can see we've made a lot of tanks over the course of the last year. We've tested a lot of them as well. We have some pressure testing capability on site. So these are all part of the NCC sort of value proposition into industry, and we see academia as playing a really strong role in providing the technology innovations up front of that. And that's sort of summarized as you can see in this sort of box here, 2027. We'd love to see some steps towards a certifiable product by design. At the moment, we're producing tanks, we're testing them, we're seeing how they fail. That's sort of this part here. We're producing product demonstrators. That's something we're able to do. The trouble is, what we produce isn't necessarily the same as what we thought we were going to produce when we first designed the tank, and that's really what this gap is designed to address. In challenge 1, we're focusing on the polymeric liners that reduce permeation of hydrogen from the high pressure tank. We want to ask the academic community, what is there in the way of process modeling or prediction of the manufacturing process of these polymeric liners that will enable us to better understand how these liners are produced, their characteristics and their performance, because as I say, when we go to test them, they're often not how we expected them to be, which means we need to go through a lot of iteration. It would be great to get to the stage where actually we design something, we're able to predict something in simulation, so that when we do produce something, it's much more in line with our expectations. Challenge 2 is very similar, but instead of focusing on the liner, we're focusing on the composites overwrap here. What we'd like to see is an understanding of how the growth of damage in these wound tanks, or potentially braided tanks, but really interested in wound tanks, how those cracks grow, and how they perform over fatigue as well. So these are really focused around the sort of digital space, design space, understanding how the manufacturing characteristics of these tanks come to affect their performance characteristics. The second gap, and this is my final slide for today, is over cryogenic tanks. You can see we've got a roadmap to 2025 and 2030. we are looking at low cycle tanks and eventually high cycle tanks that are flight worthy, so certifiable by design. So challenge 3 and challenge 4. Challenge 3 is looking at how we can predict the tolerance of the materials to these micro cracks. So what are the ways that we can toughen matrices or toughen composites in order to prevent those micro cracks from developing and also from spreading as well. We know that these micro cracks cause an issue in the performance of cryogenic tanks, because what will happen is that the hydrogen, very small molecule, can escape. It can leak into the vacuum sort of insulation around the tank, and that reduces the performance of the insulation, and then you end up with a sort of a bad positive feedback loop. So we would really like to see some innovations in materials chemistry, or perhaps just around the prediction of those micro cracks. And challenge 4 is then being able to look at the materials themselves to address the permeability issue. As I say, it affects the performance of the tank significantly around the insulation of those tanks. So what are the materials changes that we can make, or indeed the coating changes that we can make to reduce the permeability of these products? We've got aggressive timescales, as you can see on the slide. 2030 is when we'd like to get to a flight-worthy high cycle tank design and manufacture. So any and all innovations in that space would be greatly appreciated, and we're hoping that we can work together to reach that target. Those are my slides for today. Thank you for listening. I'll pass across to I think it's Steve around digital.
I can get started here. All right, good morning, everyone. So I'm not Mark, I'm at Australia. I'll take you over our interests in the digital space, what our strategy is, and the support that we're looking for from the academic community. So can we go to the next slide? So digital engineering is a broad space, but our underlying aim is to be able to accelerate the process by which we go through a typical engineering process. So starting all the way from conception through to detailed design, understanding how something is made, and then that product going into market, and even then end of life and material reclamation and so on. So being able to use some of these new technologies that are around, the technologies that are in their infancy, at least in the engineering space, to accelerate that and to make the engineering across the UK much more efficient than it is today. As an example of some of the work that we've done, I could like to point you towards the DETI program. So please go and check that out. There's a program we started close to 5 years ago now, and there's a number of different areas in that, and we've continued to develop those, and that might give you an idea of which things that we're working on and continuing to develop. But in particular, I'd like to point you to something like the 5G Encode program, which is a program looking at 5G technology in the workshop, and that's an example of how we're kind of branching out from just the pure composite manufacturing space and understanding and looking at the engineering process as a whole. So we're not focused just on the composite side of things. So those three bubbles there, design, manufacturing, and through life, we're just going to go into a little bit more detail on them. So I'm going to take you through the design one, and I'll hand over to Stephen to take you through manufacturing and through life. So if we go to the next slide. Okay, so in the design space, the 4 key areas that we're most interested in are model-based enterprise. So this is about connectivity of data across that entire product lifecycle. So this is includes digital thread, it includes digital passports. It's about communicating the data right from the design space to manufacturing, so we get confidence in understanding what is being manufactured. It's also about taking that data further and enabling some of the things like how do we go about doing material reclamation to support sort of end of life and sustainability, and that supports things like the ceramics and the tanks that we've already talked about today. There's the concurrent design systems. So this is looking much more at the detailed design space and understanding how the different design domains can be working together simultaneously. So allowing us to do a full design space exploration and ultimately doing a multidisciplinary optimization, so we can optimize for a holistic product rather than just looking at individual parts of the design problem and passing other problems sort of downstream to other people to solve. There's certification by analysis, so demonstrating the quality of our digital tools and demonstrating that they are giving answers that are suitable and ultimately that the products that we are designing are certifiable. So that includes demonstrating how good those models are and proving that we can do as much of the testing in the virtual space, thereby saving ourselves a lot of money doing the testing, doing physical testing, and also accelerating the process to get to market with a new product. And the last box, it says generative AI. Really, that's sort of expanded to sort of all AI and machine learning, and understanding. This is a really broad challenge. Understanding where exactly that fits into the design space. So particularly for the design part of the process, understanding exactly how you can use tools, but perhaps like ChatGPT, the language models, perhaps the more traditional deep learning models, to manage the knowledge, transfer that knowledge, and expose a lot of the previous knowledge that we have in the organization so that it's all upfront to the designers at the beginning of the design process. So all of that then feeds into the next phase, the manufacturing, and I'll hand over to Stephen for that.
Thanks, Amit. Hi everyone, Stephen McCartney, I'm Chief Engineer in the Digital Practice at the NCC as well. I'm going to start off by taking you through some of the themes we have around digitalisation of manufacturing. So overall, we're looking to reduce waste and cost of operation. So we're trying to hit that first time every time manufacturing. So the first theme is self-adaptive manufacturing. So this is exploring the idea that we use real-time data coming from a process to then control that process. So in the composite space, that can be looking at resin infusion and changing inlet valve pressure based on what a model or an algorithm thinks is going to happen, whether we're going to have a good or a bad outcome. So any ideas for technology development in that area would be very useful. We struggle with doing things with real-time data, getting data through fast enough, and also making decisions in the right way that is a trustable way. Because as soon as you take something out of the hands of the person in control of the process, they then don't trust the technology. We're looking also at industrial Internet of Things and connectivity. So solutions to make factories smarter, shop floors smarter. Sort of bare bones of that is a quite high TRL technology now, but it's still not very well deployed in manufacturing, and that's because it's too difficult to connect sensors to platforms to collect data, to then use that data for things. So again, it's about making the process smoother. Augmented operations. So this is about enhancing human beings in the loop, giving them instructions, giving them access to real-time help and assistance, whether that's from another person who's far away or whether it's from a machine that understands what they're doing. So it's everything around trying to help somebody do their job better. And then waste management is specifically looking at around reducing the waste within a manufacturing cell. So tracking things coming into the cell, things going out of the cell automatically, and then things like energy monitoring, weighing waste that gets developed in the cell and that sort of thing. Next slide, please, Matt. And then through life, so this is once your product's left the factory, we are one area we're looking at is structural health and usage monitoring. So this is the idea of a digital twin in the field, understanding what the product is doing, how it's operating, whether it needs maintenance now or whether it can wait for 6 months. That sort of data can really help to reduce in-life costs. But there's a huge number of issues with different data components that are in the field when they're not easily attachable to fiber optic broadband, and issues around IP and data, trying to get data from a customer when they might want to share that data and that sort of thing. Augmented in-field servicing. So once you've identified you do need to service your product, actually sending someone out to the field. When they get there, they might discover that they don't have quite the right skills for the product they've gone to service, or they get there and what the problem they discover is a 2-minute job that they haven't been trained on yet. So augmenting that, providing remote expert help, again, guided instructions, meaning they have to carry 500 manuals around with them. So digital tool in that space. And then finally, through life passports. So this actually comes last, but it joins all the three previous themes together. So everything from design through manufacturing through life, keeping data about a product. So you've got an auditable trail of every single raw material that went into the product and the raw materials, carbon emissions at that point, or the processes that happen to build the product, any sign-offs, audits, regulatory compliance that the product's gone through, and then everything that's happened to the product in life. So somebody sort of equivalent to a full car log when you buy a second-hand car. So anyone who uses the product understands exactly the life it's gone through to get to that point. Next slide, please, Matt. So across those three areas, we've got some specific areas of interest. So these are things that we could really give some help on. So the first one is human augmentation. I talked a bit about that already, but there's various ways it can be done. So you can have visual, audio, physical, including things like exoskeletons. This a bit like, we don't have AR and VR on this list, but a bit like AR and VR, human augmentation hasn't really taken off as much as it could have done in manufacturing. And we think that's because products are too expensive and they're too complicated to use. So ideas in this space to help reduce the cost and sort of have a step change in what's possible. Machine learning for manufacturing. Obviously, AI and machine learning is the current buzzword, but we really think it's got a lot of potential in manufacturing for very specific models. So not necessarily a model that costs £100 million to train, but a model that's trained on a specific process for a specific customer using for their equipment. And it might just be the example I used earlier about resin infusion. It might just be a model designed for that. But the difficulty of having so many of that is you have to have so many different models. You have to have models that can be very easily trained on specific equipment. So that challenge really is about ideas for models that can be very effective in this way, but then also for managing large-scale models that are all a bit different and how manufacturers can deploy and manage them. Engineering knowledge management is a constant problem. How you track and store your knowledge and make sure it gets to the right person at the right time. We believe that one space that LLMs could be very effective at, but again, need to prove this out. Cybersecurity of OT and IT devices in a factory. So there is a huge challenge at the moment for manufacturing. Everyone's telling they need to become more digitalized and it's going to help them all over the place. But then it hugely increases their cyber risk by having devices in the manufacturing cell that might need to be connected to the internet. It could be accessible remotely. And so cybersecurity products or cybersecurity ideas to help protect the factory, but still enable manufacturers to be flexible and digitalized. Manual dexterous task tracking. So this is related to the human augmentation, but this isn't more about watching what someone is doing, tracking their hand movements for manual tasks, and potentially using AR headsets. But again, these technologies can work well, but they're all very bitty at the moment. You have to buy lots of different components from different places, and there isn't really a consistent sort of open architecture of how to build them right. Structural health monitoring, I've already talked about that, but that's an area we're very interested in. Bringing, and then, Amit, do you want to talk about the last two on the list?
Yep. So our typical engineering process, there's normally a handover of information from the design space to manufacturing. Can we close that loop into bringing that manufacturing data back to design so we can understand what manufacturing capability really is and be able to design all the way to the limits of the capability of that? So communicating that information well in a two-directional way between two parts of the engineering life cycle. And the final point on systems engineering. So systems engineering is an established practice in engineering, but model-based system engineering is sort of much more in its infancy. So the tools that are required to do that and enable all of the things that come with that, such as traceability, through life, being able to run a digital twin and virtual simulations of assets in service. Those tools are a lot less mature, so being able to develop those to be a little bit more production ready is incredibly of interest to us. Okay, that's what we're interested in. Thanks a lot. I'll hand over to the next presenter.
And that will be me. Thank you. Hi, good morning, everyone. My name is Konstantina Kanari, and I'm working as an advanced research engineer at our Defense and Space team. Next slide, please. So I'm here today to kind of talk about the defense roadmap and strategy at the NCC. So we have been speaking with primes, we have been looking at government initiatives and priorities, and we have developed our technology strategy for composites in defense for 2024 and 2025. And this technology strategy covers primarily 3 pillars, as you can see. The first one is survivability, the second one is high temperature applications, and the third one is extreme environments. And we're looking at composite materials that underline these 3 pillars. There are certain aspects of materials, for example, sustainability or Industry 4.0, that undercut all of these strategies. However, I wanted to show you and talk about the 5 main industry priorities that keep coming up when we talk to primes and government. So the first one is composites for extreme environments. So that could mean composites are either ceramic, polymer, metal. We're a bit material agnostic at this point, and we're interested in developing composite materials that can withstand extreme temperatures, for example, from cryogenics all the way to materials for hypersonic flights, for example. Then we're looking at materials for fatigue and aging. So we're really interested in understanding how fatigue and how aging affects composite materials, especially towards the end of their life, because we don't have a lot of data at the moment and in a wide range of materials due to composites being such a new technology. Then we're looking at materials for fire, smoke, and toxicity. So especially when we have assets that contain personnel, we need to be really careful about the materials we use that can potentially be affected by fire, smoke, and toxicity. And especially when it comes to composite materials with organic matrices, that can be, well, actually fatal. So we're looking at developing composite materials with resistance to fire, smoke, and toxicity. Then we're looking at composite materials for the marine environment. So marine environment has its own specific challenges because we have, for example, a submarine that travels from a polar climate one day to a tropical climate after 2 days, for example. So we're looking at materials that can withstand a wide range of temperatures. That is not necessarily something we currently have at a high TRL level. Then on top of the wide temperatures, we're adding corrosion from salt water. We're adding the added UV protection that we need. So there are multiple challenges that kind of come into one specific topic of composites for marine. And then the last one is the electromagnetic protection. So when it comes to, for example, electronic enclosures or batteries, we need to make sure that whatever we put, whatever material, whatever structure we put on a specific asset cannot be interfered with externally. And this is something that we are really interested into looking when it comes to composite materials. And the last thing that I wanted to point out is that the one priority that kind of overcomes every single other item is that we are looking at sovereign capabilities with a supply chain based in the UK. We're currently working with the UK, we're working with supply chain in Europe, and even sometimes the rest of the world. But defense is a very specific sector, and we're kind of trying to develop any capabilities that are based in the UK. Next slide, please. Thank you. So the topics that we would like to see based on the technology roadmap that I just showed you is, first of all, like I said, following my previous point, is developments for sovereign supply chain. If you have any projects, any ideas on that, we are happy to have a discussion about this. Then we're looking at smart composites with multifunction capabilities that will add features and conductivity to laminates and surfaces. As a first example, we're thinking of metal materials or metal surfaces. But if, for example, we have a tailored fiber placement, or anything, like I said, that comes up that will provide multifunction capabilities, we're happy to have a discussion. Then we're looking at projects on high volume manufacturing for airframe on fixed wing UASs or drones, as they're most commonly known. We're looking at engineering biology solutions for smart composites or composites with increased fatigue and aging. Composite materials for use in the marine environment, as I've already explained. And then we're also looking at materials and manufacturing technologies that are associated with reducing the effects of RF and laser-directed energy on any composite materials, and materials and manufacturing technologies that are associated with repeatable low-cost manufacturing of ceramic matrix composites specifically. And this last one is kind of similar to what we're already doing with the moldable BMCs that Roger already talked about. But if you have something similar, please feel free to reach out and we can have discussion. Thank you.
Thank you, guys. Thank you, everybody. Team, Matt, Amit, Stephen, and Konstantina. Thank you for your very clear outlining of what it is that the NCC needs more, crucially right now. So just to conclude this brief overview of the Technology Pull-Through program for next year. If we can move to the next slide, please, Alex. We have had a look at how the program can transition technologies that are suitably mature from the university space into the commercial space. The benefit to UK PLC is obvious. The benefit to the academia is that this might provide a route to a demonstrable and clear impact of the research activity, which has obvious consequences for the REF framework. We've given you some examples of how TPT can promote technology and can progress technology into the real life space. And just to remind everybody, today we're going to be launching the program. The initial expression of interest can be placed in very simply. It's just a one-pager, a simple form that we're capturing today and for the next 4 weeks. After which the down selection process starts and goes through a very set of systematic stages with very clear stakeholders that will not only at the NCC but also outside of the NCC remit to get as an objective review of all the opportunities that arise from today. So if you do have any questions now on the process or on the technologies themselves, you can either ask them now. We've got 5 minutes to go through the most urgent questions, but there is also an opportunity to get in touch with me perhaps later on, and I will be able to redirect your questions to specific people if I'm not able to answer them, and in the immediate future, so that we can get the whole process kicked off. I think that there is a question in the chat from Tahir Sharif. Can we reach out to a research team leader to discuss a project idea? Absolutely, yes. That's probably the best way forward before you start putting things in writing. Again, you've got our email addresses now on the slides. You can reach out to any of us and we will put you in touch with the right people at the NCC. Just for your information, as a part of the project definition process, there will be an element towards the final stages when the whole research activity has to be scoped out and defined, and that is obviously done in conjunction between the academic partner and the NCC champion that has been identified within our cohort of engineers, so that the project that comes out ticks all the boxes for suitability within the program itself. So by all means, get in touch by email later on today, and we'll put you in touch with the relevant person. I've got a question from Emil. Can you confirm the foreground IP is shared? This was not the case last year. So that is a very good point that you raised, Emil. Thank you very much. The situation from last year hasn't changed, and I apologize if the language might have been misleading. So just to clarify, the background IP stays with the rightful owners at the date of the start of the project. So all the background IP that is declared, obviously, before the project starts, that is owned by the academic partner stays with the academic partner, or the IP that's owned by the NCC stays with the NCC. Anything that is developed further after that is shared in a sense that the ownership stays with the NCC because the NCC is funding the activity, but the academic partner retains I can't remember exactly the wording now, but it's effectively a free license, a perpetual license to use the foreground IP for research and teaching purposes. Also, what the agreement, the research agreement states is that if there is any commercial exploitation coming out of the technology pull-through program, which thankfully is quite often the case, and we want that to be the case, then the parties, so the NCC and the academic partner, will have to reach an agreement, a fair agreement that takes into account the contribution to that particular technology from both parties. That has been put in place as a clause, if you like, in the collaboration agreement to take into account, for example, the fact that either the NCC or the academic partner might have a lot of background IP that dates back, I don't know, 2 decades of research that they are potentially bringing into this commercial spin-off, and that needs to be taken into account. So there isn't a single sides that fits all possibilities. We have put in writing that commercial exploitation will have to be discussed on a case-by-case basis, and you will take into account all the contribution of the individual parties to the specific activity. But that's a very good point. Thank you for raising that, Emil. We are bang on time, so thanks to all the speakers for being very timely and keeping to the time scales. Again, if you've got any future questions, drop us an email. We will be adding the webinar, the video, the slides, and all of our contact details, as well as a frequently asked questions list on the technology pull-through page of the NCC website that you can easily find by Googling it. So just go back there if you need any further clarification for what's been discussed today. Thank you all for coming and attending today. I hope that this is the first step for another year, another round of very exciting proposals discussion this year, and I will hopefully see you soon.